All right, everybody. This will be AP Chemistry Notes, pages 41 to 44. And last unit, we did delta H. And we're going to go back to that for a little bit. And this time look at a little more closely what's going on when a solution is formed. The easiest example to use right now is, as I talk about it, just imagine sodium chloride is dissolving into water. And that'll be a good example to have in your head. There are three things that have to happen. The solute, in this case the sodium chloride, it has to break the attractions amongst itself, and that will be endothermic. The solvent, in this case the water, has to break its attractions. That's endothermic. And then there'll be some new attractions between the solvent, the solute, and that will be exothermic. Now, in the case of sodium chloride, breaking these solute-solute interactions, that's what's called, you're having to break the lattice energy right here. And lattice energy has to do with the idea that you have a sodium ion and a chlorine and then a sodium, and you would have something like this. And this is referred to as a crystal lattice. And these ions would be going in all three dimensions, but I'm only going to draw it in two dimensions. And because it's this repeating pattern like this, that's the lattice. And there is a certain amount of energy that's holding this together that has to be broken. And that's the lattice energy that's referring to right here. In our case, the solvent-solvent would be intermolecular forces, which water has fairly strong intermolecular forces. And then the overall enthalpy of solution will be based on adding these three things together. And so I found this diagram on the internet. It's a little blurry, but it should help. What they've done is they have the solvent and the solute being broken, and notice these arrows are always requiring energy. And then they have the new interaction between the solvent and the solute here. And notice that's always exothermic. And the question of whether the overall process is it has a positive or a negative delta H just depends on how these values add up. In this picture on the left, they have the total amount of energy for both breaking the solvent and the solute. And in green, I have the new interaction. And in this case, you can see that the overall result will be this. And so this would be an exothermic situation. Over on the right picture, the total is about the same. It's a little more. But more importantly, in this case, the new interaction that I have in green is not, I mean, it is giving off energy, but not that much. And so the result is here, and that is a endothermic process. And I give an example. Ammonium nitrate, if you just take this, it's ionic, and if you just put it in water, this is actually endothermic, the overall process. So if you did this, let's say in a beaker, and held the beaker would get cold because it's requiring energy from the environment, and so you would fill this. And this is actually used in cold packs. Sometimes emergency and first aid kits have a cold pack, and normally the cold pack is just a mixture of ammonium nitrate in a little sealed pouch, and then water in a separate sealed pouch. And then when you go to use the cold pack, you just break those pouches or break one of the pouches so that the two things come in contact, And it's just ammonium nitrate dissolving in water. Simple process, but it gets cold. The opposite example I have here with potassium hydroxide, in this case, it gets hot. And so if you had this in a beaker and you dissolve potassium hydroxide or sodium hydroxide in water, it actually would get warm to you as it gives off that excess energy. And this is actually something I have to be careful of. Sometimes when I make a solution like potassium hydroxide or sodium hydroxide, it gets so hot that steam starts coming off of it. And of course, the steam has a little bit of the chemical in it, and you don't really want to be breathing potassium hydroxide or sodium hydroxide steam because those are strong bases. And let's just say your lungs don't like it. All right. I mentioned this thing over here. I haven't heard about it recently, but a few years ago, there was this thing called the Salt and Ice Challenge. And it was a silly thing that kids were doing. And unfortunately, some kids really hurt their hands doing this. And what you would do is, I'm not telling you to do this, by the way, but you would put salt on the top of your hand, not in your palm, but the other side. And then you'd set an ice cube on it and see how long you could take it. That was the challenge, was how long before it hurt too much. But the problem is, this situation, it's actually colder than if you just put an ice cube on your hand. And the reason is because of these first two steps, right here and right here. That's why it's so extra cold and hurts. And unfortunately, some kids were doing it for too long and it was actually messing up their skin. I had a student that showed me once. They had a permanent scar from it. So don't do that. Moving along, as I mentioned, if you want to find the delta H of the solution process, you can just add up all three things. There's another version that I have down here, right here. This one takes a slightly different approach. There's something called delta H of hydration, and it combines the second and third step together. And then the first step is just breaking the lattice energy. And so you just have to include that here. And so this is a different way. And I don't have an example here, but the calculation is pretty straightforward. If you're given these three, you just add them together. If you're given lattice energy, just flip the sign and then add the delta H of hydration to it. But otherwise, it's pretty straightforward. You'll see it in the homework. Now, one of the possibilities of the new interaction between the solute and solvent is what's called an ion dipole. And again, let the name help you. The name tells you what it is. It means there's an ion and a dipole. The ion will either be Na plus or Cl minus in my example. The dipole will be the fact that water is polar. And so over here on the left, I have before the solution is made. So we've got solid NaCl and we've got liquid water. And then when this dissolves, the ions separate, which we've already discussed. And what has to happen is the ions have a desire for the opposite charge. And so notice how the water molecules orientate themselves around the Na+. It's the oxygen side of the water, as I have it drawn like this with oxygen here and the hydrogens, like that. But rather than actually putting the atoms, I just drew this little, looks like a, kind of like a Mickey Mouse, but the ears are a little too small. Anyway, the oxygen side is the negative side of the pole, or of the polarity. And so that's the side that's attracted. Notice the way I've orientated all of them. Now I just drew 4 to show the pattern. How many there are depends on the situation. And of course, this would happen in 3 dimensions, not 2 dimensions, only like I've drawn it. In the case of the Cl minus, water will orientate the opposite orientation, where the hydrogen or positive pole is closest. Of course, if the ion has a higher charge, like a +2 or a -2, it's going to take more water molecules to satisfy that need. The size of the ion also affects things, and we'll be looking at that a little later. So I say here, why do solutions become saturated? In other words, why do you reach that limit? Shouldn't you just be able to keep adding more salt forever? Well, the reason is you run out of waters. It takes a certain number of water molecules to surround each ion, and eventually all the water molecules are busy and there's not enough. And this actually reminds me of something I remember not understanding as a kid. The house I grew up in has a swimming pool. And of course, my dad would take care of the water, and he'd always be adding things to the water to keep it like you're supposed to. And eventually, it seemed like every few years, he would drain the entire pool, which took a while. He'd refill the entire pool and start over. And I remember thinking that was silly as a little kid. And I was thinking, why is he taking all that time and wasting all that water? Well, the issue, I now understand, of course, was that the water was getting saturated. It had so much chemical in it. Adding more chemical really wasn't going to do anything. And so you had to start over. And of course, now I know. I mentioned here, why doesn't NaCl dissolve in oil? Well, oil is nonpolar, and it can't provide this opposite charge like in the situation we have drawn here with the ion dipole, and that's why it doesn't work. Next page. Again, colligative properties, moving to a new topic, is based on the number of particles, or more specifically, the number of dissolved particles, but it doesn't matter who they are. It doesn't matter whether it's ionic or covalent or polar or not, or what the charge is, or the size of the molecule or anything like that. It's just based on the number. In other words, the more particles you have dissolved, the more intense the property. Now, one of them is that the vapor pressure of the solvent gets lowered. So this really should be, it really should say solvent vapor pressure goes down. And this makes sense because if we stick with our example of dissolving salt in water, water has a vapor pressure. Solid salt doesn't really even have a vapor pressure. So it's the solvent we're talking about. And so if you imagine a closed container, let's just do water again. Most of the water is going to be down here as a liquid, and a few particles will escape and start bouncing around, and those particles will create the vapor pressure. Well, if you put a solute like sodium chloride, I've tried to draw that here. Let me use a different color, make this more clear. Let's do red for the salt. We've got some here, 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 and here. What happens is these interactions between the solute and the solvent make it harder for the solvent to escape. So you don't get as many particles, and I've shown that by just drawing two waters in this case, and that's why the vapor pressure goes down. Now notice I said non-volatile solute. If the solute is volatile, meaning the solute itself has its own vapor pressure, well, now you have a different situation, and we'll talk about that later. Okay. You look at this picture here. This is an interesting scenario that I don't think you would expect to happen. So let's say you have water here, just pure water. So this. And then over here on the right beaker, right here, so I'm still in the left picture, but the right beaker, right here. Let's say this is a solution of something. So we could do salt water. You would think if you put this in a closed system, meaning can't interact with the environment, you would think that the water in the left beaker would stay as it is, And you would think that the solution would stay as it is, but it doesn't. Over time, the pure water will make its way over here through the vapor phase, and eventually, other than a few water vapor particles bouncing around like this, all the water would slowly make its way and end up over here, and you would actually see the volume of your solution increase. And the reason this is happening is because the vapor pressure of the pure water is higher than the vapor pressure of the solution. And so the solution will have a vapor pressure, but it won't be as high. And so what happens is the pure water keeps pumping out more water into the atmosphere of this closed system, and then it slowly gets absorbed by the solution until there is no more pure water. Or if you had two solutions, this would happen until they ended with the same concentration. Now, this happens very slowly. It does actually happen. And so at school, I'm going to set up this system. I'm not going to use salt water and pure water because it goes way too slow. I'm going to use concentrated sulfuric acid on one side. So I'll have a beaker of concentrated sulfuric acid, and then I'll have a beaker of pure water or distilled water. I'll put the whole thing in a closed container so we can see it, and we'll wait. It'll take a while. I call it the longest demo ever. And what will happen is the water will make its way over there, like in our picture. All right. As always, there's a mathematical equation. I think I just messed up my notes, but that's okay. I'll fix it in a minute. Let's see if I click off there. Whatever, I'm just going to zoom in. Work with what I have right here. There's a mathematical equation that will help us calculate the new lower vapor pressure. It's called Raoult's law, named after a French guy. I like his first name. His first name was Francois. So that's a fun name. Anyway, it says the new vapor pressure, or you could just say VP new, is equal to the mole fraction of the solvent, because remember, it's the solvent we're talking about, multiplied by the solvent's normal vapor pressure. And in the case of water, we've already done that. We looked at that on page 20 of the notes. So I'm going to reference that page, that chart. And there's something we have to add to this. When you do the mole fraction, it's going to be the total moles of water over the total moles of everything. When you do this, you have to factor in if the solute splits into multiple pieces. So notice I've got moles of water on top here, and then the complete total moles of everything is the moles of water again, so the same thing, plus the moles of solute multiplied by what's called I, or its fancy name is it's called the Van't Hoff factor. It's named after another guy with a great name. I'm sure I'm going to say it wrong, but his name was Jacobus Henricus Van't Hoff. And he, if I remember right, he was Dutch. And he was the very first Nobel Prize winner in chemistry in 1901, if I remember right. So that's kind of an important person there. Anyway, this I value is named after him. And the I value is how many particles something splits into. So if we go through some examples, you'll see sodium chloride, it splits into a sodium and a chloride. So that's 2 particles. So it has an I value of 2. In the case of glucose, the molecules separate from each other, but they stay intact. So they don't split into pieces. So the I value is 1. Calcium chloride, it splits into calcium and a chloride and a chloride. So that's 3. Most covalent things are going to be a 1, but acids get a little tricky. So I have 2 acids here. In the case of a strong acid, we just assume that it completely splits. So in the case of HCl, it would be a value of 2. But in the case of a weak acid, like hydrofluoric acid, it only partially splits, which means its value right here, it's going to be more than 1, but it's not going to be a complete 2. And it'll be somewhere between 1 and 2. It'll actually be closer to 1. The weak acids typically don't split much at all, and we'll study that in detail later. So as of now, we just need to know that it's somewhere between 1 and 2. All right, next page. Oh boy, things are moving around on me here. That's better. All right, this first example is really similar to the second one. So you're welcome to do the first one, but I'm just going to go right to the second one because it'll be good enough. And it's a better example. So I normally just skip that first one, as you can see. What is the new vapor pressure of water? So again, we're focusing on the solvent here, if this much sodium chloride is added. Well, the equation is that the new vapor pressure is going to be the mole fraction of water times the normal vapor pressure of water. So what I need to do is I need to look this up, and I did already on page 20, it's 23.8. Then I need to find this mole fraction. So I take my grams of water and turn it to moles, my grams of sodium chloride and turn it to moles. Here's the mole fraction symbol. Here's my moles of water. Here it is again, I value of 2, and the moles of the solute. Now, sometimes students say, do we really have to do the I value times the moles of solute, or can we just use common sense? Well, no, not common sense, but chemistry sense. And can I just know to multiply the moles, the 0.55 by 2, and that would give me my so many moles of ions? And that's fine. That's basically what we're doing. The I value just kind of does that work for you. But if you just want to use your knowledge of the system and do that, that's fine. In this case, the math works out that the new vapor pressure is 22.8, which is a little bit lower than 23.8. So you see it doesn't dramatically affect it, but it does lower it a little bit. All right, next one. In this case, it's a similar situation, but I'm asking for molar mass. So you want to think, what is molar mass? Well, molar mass is always going to be so many grams per so many moles. Well, 1 mole once we do the math. So in this case, it wants to know the molar mass of the something called carbonic diamide. I think I chose that just because it sounds cool. I don't know what it is. And at first, it doesn't seem to be related to this concept. But what we can do is, because moles is in this calculation of Raoult's law, we can use it to find moles, and then that helps us find molar mass. So you'll see at the end, when I solve for molar mass, I've already got the grams. We knew that right here. That's in the very beginning of the problem. And we're going to use Raoult's law to find the moles of carbonic diamide. Now notice it said non-electrolyte. Non-electrolyte means that when it dissolves in water, it doesn't conduct electricity. And that's a fancy way of saying that it doesn't split into pieces. In other words, the I value is just 1. So whenever you see that non-electrolyte, that's saying I value of 1. In this particular case, on another discussion, it might have actually something to do with conducting electricity or not conducting electricity. So it says the observed or new vapor pressure is 22.67. So that I plugged in there. The normal is the same as the prior problem, 23.8, and I solved for my mole fraction here. Now you need to define what that is. The mole fraction of, in this case, sorry, I might have misspoken earlier. We're solving for the molar mass of the carbonic diamide, but it is the solute. The solvent is water again. I might have misspoken at the beginning of the problem about that. The mole fraction of the water is again going to be the moles of water divided by the total moles, which is moles of water plus the moles of solute, in this case multiplied by 1, or just don't even bother putting the 1 in there. And we can find our moles of water because we were given the grams of water, so I got the moles there. So you plug everything into the mole fraction. We know that the mole fraction from earlier is 0.953, so I put that here. I know my moles of water, I put it here and here, and we're solving for that. I abbreviated it CD for carbonic diamide. And once you go through the math, you get the moles is 0.346 with an extra sig fig. You finally get to molar mass here at the end. And so we've got our grams from the beginning of the problem. We just solved for moles, 0.346, and you get 58 grams per mole. And again, molar mass is a rare time in chemistry that you can actually do a sanity check and see if it makes sense. And so, okay, 58 makes sense because that's a reasonable size for a molecule. Of course, if you get 0.01, you know that something's wrong. Next, kind of like with ideal gases, you can have this concept of an ideal solution. And if a solution were to obey Raoult's law perfectly, it would be considered an ideal solution. But of course, things are never ideal. They're never perfect. Just like with the ideal gases, real gases are not quite ideal. And so here are 3 reasons that a solution will not be ideal. First is we are assuming that the solute is not volatile, like sodium chloride or sugar. Well, the solute could be volatile and it will create its own vapor pressure. An example of that would be acetone in water. Acetone, most people know as nail polish remover. Well, that's actually more volatile than water. So if you mix that in water, it's going to create its own vapor pressure and lead to a false result that is higher than expected. Often you can have very strong interactions between the solute and the solvent, so that will lower the vapor pressure even more. And there's a handout I'm going to have you read that's in our packet of worksheets, page 598 and 599. And third one, and I find this one actually to be the most interesting one, is I mentioned the I value, the Van't Hoff factor. Well, it turns out that is assuming that things completely split perfectly, but they don't. They might mostly split, but they never quite split perfectly. And so it turns out our I value is often higher than it should be, which leads us to calculating a higher value than we should. And so here's an example. Take sodium chloride. We said it has an I value of 2. And that's the best we can do without knowing anything else. But as the concentration of sodium chloride goes up, what you have happen is you still have sodium ions and chlorine ions, but you also end up with situations where they don't split perfectly, and you might still have a pair of them together surrounded by water molecules. Or you might even have a little chunk of a few of these ions. And so the I value is actually less. And I looked it up. An NaCl solution with a molality of 0.5, its I value would actually be 1.8 and not the 2 that we would have used in a calculation. A little review question. Why does vapor pressure go down? Which was kind of the theme of today. It's because the solvent has a harder time escaping than usual. And in the homework here, you'll see it's a few problems in the book. Read the handout that's in our packet, and it's a very short worksheet called the Solution Formation Worksheet, in which you're going to get a chance to actually calculate the enthalpy of solution forming. Again, it's fairly simple. Just look back on, it was page 41 if you need to see those again. And that takes care of this lesson.